All right, so the objective here today is to demonstrate some of the basic capabilities of Simulink to model dynamic systems and control them. And specifically, we're going to be trying to adhere to the design standards that we want to use for the big simulation for the Cyclone Robosub controls team. So we're going to start by describing the model we're going to be simulating, and then we're going to build that model in Simulink, run it, and then build a controller for it as well. So to get started, let's describe the system we're considering here. A basic system for dynamics modeling is a mass spring damper, where I have a damper that slows down the block whenever it moves. And I have a spring that keeps the block oscillating back and forth once it's displaced from equilibrium. We could also apply a force to this block, think pushing or pulling it, that I'll just call F. Neglecting friction, this spring and this damper fully control our system in response to the force F. So if we write down the equation of motion for this system, we'll start with Newton's second law, which states that the sum of the forces is the mass times acceleration. Thinking back to intro physics, the force done by a spring is k times x, where x is the position of the spring. And the force done by a dash pot or a damper is bv, where b is the damping constant and v is the system's velocity. And that's all equal to ma. What we're after for a dynamics model is a function for acceleration. Because if I take acceleration and I integrate it, I can get my velocity. And if I take my velocity and I integrate it, I'll get my position. So what I can essentially do, as long as I can find my acceleration at any point in time, I can figure out where I am and how fast I'm going based on that data. So with that objective in mind, let's go ahead and rearrange this equation for the acceleration. Solving the acceleration on the left-hand side, we'll get negative k over mx minus b over ma. And there's one more force I didn't add, so I'll go ahead and add that now. We could also have that forcing F. So I'll add it to this side of the equation as one of the forces, and I'll add it to this side of the equation as well. All right, so here I can see my acceleration is dependent on the force that's applied. That one makes sense. The force the spring's applying, which is a function of how far I am from equilibrium. And, oh, that should be a v. And the velocity, based on how fast my block is going. Now, we know that velocity is the derivative of position, and acceleration is the second derivative of position. So I can rewrite this expression like this. The second derivative of x is f plus negative k over m x minus b over m dx dt. So this is the differential equation that describes the motion of our system. Finally, I can go through here and I can replace all the derivatives with the standard notation for derivatives in a lot of physics textbooks, which is to replace a double derivative with two dots, x double dot we call it. X is left alone. And this dx dt just becomes x dot. So whenever we see x double dot, that's the acceleration. And x dot is my velocity. The other thing this equation gives us is what the state vector of our system should be. The state vector is the minimum vector to describe how the system evolves with time. In this case, it's everything that's a function of position or velocity on this side of the equation. So I can fully determine what my state of my system is just based on the position x and the velocity x dot. So we clearly don't want this notation where x is a function of x. So to denote this state vector as something different, we'll put a bar over it like so. Now you might say, hold on a second, the force also affects my evolution over time. It affects my acceleration. But we don't include that in the state vector. That's included in our input vector, which in this case is just the force F. What we're ultimately going to try to do is change this F in such a way that we drive the position and velocity to values of our choosing. So my job then is to build a simulation that takes x and x prime and uses them to calculate the acceleration. And then once I have the acceleration, it integrates the acceleration to get x and x prime at the next time step. So I'll have this loop that'll keep going through to propagate my system forward in time. And that's what a simulation is essentially doing. So our algorithm will look something like this. I'll have my state x double dot, and this state x double dot is going to be a function of all the states of the system that came before it and the forcing. So I can visualize that with a block diagram. Let's see here. So going into this block diagram, I'll have my forcing, F. I'll have my position, X. And I'll have my velocity, x dot. So this position function will go inside this box here. And this is representing the system's dynamics. And in control theory, we call that the plant. All right. And this block is going to do some math for us. And then it's going to output this state vector, or this acceleration, excuse me, x dot, double dot. All right. Once I have that, we know I just need to integrate this. And that will give me my x dot. And then I integrate it again. And that will give me x. All right. So this system is not a full loop yet. It doesn't go back around to itself. And the way we make it do that is just by connecting these signals, x and x dot, back to the other side of the equation. So I'm going to bring this all the way over here. And you can see now how this little loop works. So whenever we're making a simple Simulink model like this, it's very helpful to draw it out on paper first. So you can worry about the layout before you get into all the complicated functions that you're going to have in your Simulink model. All right. The last part of our system that we'll develop is the controller. The controller has to decide what force to apply in order to get the system where we want it. So the controller is going to be another box up here. Controller. And we know the controller has to output this force F. Well, what does the controller input? The controller has to know the position we want. And I'll call the position I want x star. Again, that's a fairly common thing you'll see in textbooks. And then I also have to tell the controller where I am right now so it can figure out how to manipulate the force. So I have to put in the same things I put into the plant. I have to put in x, and I have to put in x dot. So my diagram's getting kind of crowded. I'll go ahead and bring x dot over here. And to show that I'm kind of crossing this line here, I'll do this little notation. And then I also need to grab my x. So I need this as well. And of course, we also want to show that this is not the same signal, it's just crossing the other signal. So it's like that. All right. So do we have to write out the system in this form? No, but it basically gives us a recipe for all the pieces of this system we need to build in order to simulate it appropriately. What we could do is just write this all in basically a giant file and then use a numerical integrator to solve it. But Simulink abstracts a lot of that manual integration for us and just lets us focus on the stuff we care about, which is the mathematics in the controller. So now we're going to go to Simulink and we're going to build this system. All right. So here I am in MATLAB 2024 B. This is what it should look like when you first load it up. The first thing I'm going to do is I'm going to rearrange it in a form that I think is slightly easier to use. So over here on the left-hand side, I have these various tabs I can open. I want to make it so the tabs that I use the most are always available. So what I'm going to do, I'm going to right-click on this and I'm going to hit Open More Panels. Depending on what I'm doing in MATLAB and Simulink, I'll want a different set of panels, but there are a couple that I always want open. The first one of those is the workspace. So I'm going to click workspace and you see it gets added right here. I like the workspace up here in this corner, so I'm going to move it over there. All right. What the workspace is going to do is going to show us a list of all the variables we currently have in use, so we can go ahead and be keeping track of them. The next thing I need to do is I want to get out the panel for the test browser, which I can see right here. And it pops it right there. I don't really love that right there, so I'm just going to rearrange slightly so my workspace is above my test browser. So what the test browser will let me do is quickly run a whole bunch of checks on my code to make sure everything's working properly, which is a big deal for really big projects where it would take a long time to check each function yourself. All right. The other thing I like to have open here is my project manager. So it's this little box right here. Let's see, there it is. And I don't like how it just got rid of the files for that, so I'm going to go ahead and drag files back onto here. So I have files and my project. The file system is very useful because, as you'll see, a lot of MATLAB stuff, you have to manipulate various file locations for various functions. All right. The last thing that I care about looking at a lot is the source control. I want to make sure all my stuff is backed up to GitHub properly. I'm also not a huge fan of that being in its own separate tab. So what I can do with this is I can just drag it onto this pane. And so now I have source control, project, and files over there. And I have workspace and test browser over here. So what you can do in Simulink, you can go to layout right here, and you can save current layout. This is the loadout I like, so I'm going to call it best layout. Now, depending on your monitor size, there might be a different setup that works better for you, or depending on how many windows you're using for whatever your current task is. All right, so all that aside, I'm going to go ahead and create a new folder to work in. I'm creating it inside my GitHub folder so I can back it up later, and I'm going to just call that folder Simulink Demo. You can create this folder wherever is convenient. Once you've created that folder, you can go open it up, and you'll get this nice blank workspace. The first thing we're going to do is we're going to create a new project. What a project does is it keeps track of all the files that are considered part of the project and manages difficult things like dependencies for you. So I'm going to hit New Project button over here in my Project tab. The other way you can do that is just by going to, actually, no, it's actually gone. There used to be a button up here, but I think it's been moved to the sidebar now. All right, so yeah, I'll open the project sidebar and hit New Project. It's going to, by default, have the same name as the folder that's in, and that's fine with me. I'll take it a few seconds to load here. All right. So it prompts me to set up the project. Let's see what that's about. So in this menu, what it's prompting me to do is describe my project. So I'll say it's a simple example controller to teach Cyclone Robosub members. And then it shows the project root is just the folder it was created in. Now here's some of the more useful features. It also offers a search path right here, which basically means I can add folders to what MATLAB can see. The reason this is useful is if I have a whole bunch of useful functions that all live inside one folder, I don't want to have to rewrite all those functions in each new piece of code I do. So the better way to do that is to put all those common functions in one folder and then use the search path right here to make sure they're automatically added to your path. You can also do task automation here, like running startup and shutdown files. We won't do this in this demo, but it's useful to know it's here. And we can also do all kinds of other custom tasks and features that are more important as you do more advanced stuff. So I'll hit apply there. And I can see it created this Simulink demo.prj object, and it created a resources folder. We don't mess around with the resources folder. That's just a folder that Simulink uses to keep track of all the data that is associated with this project. Let's start building our controller. I needed two different things in my controller, in my system, I should say, a controller and a plant. So I'm going to go ahead and create a new Simulink model to put those in. The way you do that is you right-click, go to New, scroll down to Model, and it'll take it a second, but it'll open a dialog that looks like this. I want just a blank model, so I'll go ahead and click that. All right, it opens up as just a blank screen like this. Let me see if I can make the font a little bit bigger here. Yeah, I'm not sure how to make the font bigger from the Simulink menu. Maybe it's an environment, preferences. Here we go. General, editor. Okay, there's apparently no way to change the font, but that's okay. All right, so the first thing I'm going to do is I'm going to create two subsystems. I know I'm going to have something called my controller, so I'm going to highlight a block right here, and I should get this little blue menu at the bottom. And one of these says subsystem, and I can just click it. So it creates a block that looks like this. So a Simulink subsystem is basically just a grouping for you to visually understand parts of your code. It has little effect, some effect, but little effect on the actual execution of the code. You could build your entire model in just a single subsystem, but it's often helpful to have multiple subsystems. So what I'm going to do is I'm going to call this subsystem my controller. I know I need another subsystem. I need the plant. So I'm going to create that too. So what I can do now, let me make these the same size. What I'm going to do now is I'm going to go through and I'm going to add all of the information we need for all the different inputs and outputs to these blocks. So looking here, I have one little input called 1 and one little output called 2 here. So if I go into this block right here, I can see there's just this input being routed straight to the output of the block. I want two more inputs, so I'll double click. When you double click, it opens this little dialog right here, and I'll just type in input. Actually type in, there it is, and I'll click that. And it automatically makes my input 2. I'll do it again, and there's my third input. This block only has one output. So I'm going to delete this trace in the middle. And so now Simulink does not know what output I should map to the input and how that mapping occurs. So that's what I have to tell it. I'm going to start by naming all these. I know the plant takes in my force F, it takes in my position X, and it takes in my velocity dx dt. I'll just abbreviate that dx. And then it's going to output the second derivative, which I'll call ddx. It's implicit here that the derivative is with respect to time, if I don't explicitly say. So now I need to somehow put all the math in here that represents the transfer function for my pendulum, or the dynamics equation. So I'll go ahead and write that in an annotation to remind us what it was. We found that the second derivative was equal to the force minus these constants k over m times the position x minus the constants b over m times the constants times x dot. Make that a bit bigger here. So this is what I have to build. Now there are a lot of different ways to do this in Simulink. The most simple way you could do this is by building up a lot of different math expressions with all the math blocks Simulink has. Simulink has blocks for plus, times, oops, that's times stamp. I think it's called multiply, divide, and so on. And what you could basically do is you could route all these traces around to basically build this equation, this right-hand side of the equation, and just pass that signal to the left-hand side of the equation. I might show that in a different demo, but that's really tedious. The much smarter way to do it is to delete all those blocks and just bring in a MATLAB function. So what this lets us do, it lets us skip all the block diagram stuff for the actual mathematics and just use the block diagram stuff for our information flow and our organization. So this MATLAB function lets me call an arbitrary script stored somewhere in my MATLAB project that acts on these various variables and computes what the output should be. So if I go inside this function by double-clicking it, I can see it has a little template for me. I'm going to replace the x with my output, which I know should be ddx. And I'm going to write what my inputs are, which in this case are x, dx, and f. So now here I can just type in my equation. Let's glance back to what it was. In fact, I can actually just copy it right here. We have ddx equals f minus k over m times x minus b over m dx. I'll put a semicolon at the end of it, which in MATLAB stops it from printing that output to the workspace every time. So there's a problem. I haven't told Simulink where to get these b and m constants yet. So I can add those as additional arguments to my function right here. So there's a couple ways I could do this with all these inputs. I could define my constants right here by using constant blocks and just write them in right here. But that's not a very elegant way to do it, and it also clutters up the workspace a lot. So I'm going to delete that for now. What I'm going to do instead is I'm going to take a look at these two variables I need. I'm going to go to the Edit Data tab in the top left. I can see over here on the right now there's a list of all the variables I'm inputting to my function and what the port is. So I want to take these two b and m values, and I'm going to click on this little type right here. And I see the options are input data, output data, data store memory, and parameter. I know these b and m values shouldn't change, so I don't really care about inputting them into the function every step. So I'll just make that a parameter. Same thing with m. I'll make that a parameter as well. I can close out of the property inspector, and my function now looks like this. So it still has the input showing up right here, but if I go back outside, I see those ports are gone. Instead of looking for those variables as input traces, MATLAB will instead look in my workspace and try to find those variables there. So a little bit later on, I'll show how to put those variables in the workspace for us to work with. All that's left to do is to route my input ddx right here and route all my inputs here according to the right name as well. All right. I'll call this MATLAB function dynamics. All right. So let's go back out here. We can see it's filled in a nice little preview of what's inside that block. If we want to see that, that's great. If we don't want to see that, I can right-click on the block and go to Format. Where is that? Format. And I can see there's options here to rotate the block, and there's also options for content preview. If I click that off, it just makes the block blank. I don't really like that, so I'm going to put it back. Format, content preview. There we go. All right, that's my dynamics. The controller I'm going to leave alone for now. because I want to just make sure my dynamics are correct before I start working on a controller. So the way we can get this to be out of the way, I'm actually going to make this whole thing commented. And I'm going to go over here and I'm going to hit comment out, which is the percentage symbol. And this block becomes semi-transparent. That means Simulink will ignore this block. It'll just pretend it's not there. All right. So I want to test if I did a good job with my plant model here, but I still need to integrate my acceleration to figure out what x and dx should be. So what I'll do is I'll add an integrator right there. So the integrator has the symbol 1 over s. That's because of the Laplace transform notation. But we don't really have to care how it's defined here. We can just grab it like that, and then we'll add 2 of them. So when I integrate d dx the first time, I'll get dx. And when I integrate it the second time, I'll get out x. So I can take this signal for x, and I can route it all the way back to here, like so. And now I can also take dx, and I can route it all the way back to here. All right, so this is my model without the controller. I want to just test this without any force right now. So I'm going to go ahead and create a constant right here. I'm going to make that constant a 0. So the force input is always 0. And there we go. So what this will essentially do is just simulate our mass spring damper without any of the control applied. We need to make sure this works before we can control the system properly. A couple other things we need to do while we're here. The first one is to go into these integrator blocks and specify an initial condition. I don't really know what I want my initial condition to be yet, and I want to make it easy to change. So rather than hard coding it inside here, I'm going to just add the variable dx0 for the initial velocity. Now it's red because it can't find that variable, so we'll have to add that in a minute. Same thing here. I don't want position to start at 0. I want it to start at whatever I specify. I'll call that x0. I'll hit enter. Again, it turned red. That's not a big deal for now. All right. One other thing I'll do while I'm here, and I'll do this whenever I'm creating a Simulink model. I'll go over to the gear icon here. And what this opens up is a dialog that I can use to choose all the parameters of my simulation, like how it's actually simulated. I can see there's the simulation time from 0 to 10 seconds here. I want that to be a variable as well, so I'm going to call that tspan instead. And then over here, I can decide whether this is a variable step or fixed step integrator. I'm happy with variable step. And I have to also decide what solver to use. These are all different solver algorithms. Most of them will work just fine. Usually MATLAB will do a good job with the auto you select. I'm going to leave it like that. One thing I do want to change here, if I go into solver details though, are these tolerances. The problem with this tolerance of 1 to the negative 3 is that for very small motion, my graph will look really chunky. So I'm going to go ahead and up this to 1 times 10 to the negative 8. In MATLAB, the little e there is for scientific notation, not the exponential e. And I'll just leave my absolute tolerance as auto. So now I'll hit apply and close out of that. All right. I would like to run my simulation, but I know it's not going to work yet because I haven't specified those 2 initial conditions, and I also haven't specified these 2 parameters. So I'll have to go do that. So the first thing I'm going to do is I'm going to go back to, I'm going to save this first of all. Let's call it mass spring model. And it'll take it a second to save. The first time you save it, it has to save the entire set of metadata for the model. But on subsequent saves, it should be much faster. Because it just has to save the things you changed. Okay, it's done now. I'll minimize Simulink. And I see now there's a mass spring model in my folder here. The next thing I need is I need a way to specify all the constants. So I'm going to hit new and then script. And I'll name this script constants .m. All right. With this folder, this file, I should say, I can open it, and I can define all the constants I need here. So the constants I care about are mass, which I'll call m. I'll initialize that to 10. And let's say I also want spring constant, which I'll call k. And let's initialize that to 100. We'll have to play around with these values to see what looks physically reasonable. So the spring constant is in newtons per meter, and this is in meters. All right, that's all the constants this particular model has, but you'll find more complicated models can have dozens of constants in here. I'll go ahead and close this out. All right, next thing I'll do is I'll create another script, and this one I'll call init. So init is short for initialization, and this is the script that I'm actually going to run my model from. What I could do is I could go into my model and hit the run button here, but I would like to be able to run my model for lots of tests without actually having to have the model open, so it's much nicer to call it from a script. So what I need to define in my init are initial conditions, simulation parameters, and then I need to actually run the simulation. All right, so for the initial conditions, I needed to define my x0, and let's just say I want that to be 0. And I need to define my velocity initial. Let's make 0 as well. So this will be a pretty boring pendulum because it will just have no change in position and no initial speed. So it should just stay at equilibrium. This is a good check to make sure we did my math right. If I make these different values and the pendulum starts waving all over the place, I know there's something wrong. Simulation parameters are things that are specific to this instance of the simulation that I'm about to run. So in this case, all that I need is the t-span. Now let's set that to 10. This is useful if you want to just do a quick check to see if your model compiles. You can limit the t-span, or if you want a really long run, you can up this. You can also make the t-span infinity, which makes your model keep running until it is terminated. This is not very useful if you're just running it from a script like this, but if you're trying to use your model to control actual hardware, like for hardware in the loop, it's good to be able to do this. I'll make that 10 for now. You could also have other stuff here, like your relative tolerance, your absolute tolerance, or the time step of your actual simulation. But we don't have any of those right now, so I'm going to just delete all those. All right. Now I actually have to run the simulation. And the way I do that in Simulink is with the sim command. And it actually already prompts me for the file, but I can also navigate to it if it's in a different folder. And I'll just put a semicolon there to suppress the output. All right. Let's see what happens if I run this. Missing parameter b. So that means I didn't make it in my constants file. Oh, actually, we just need to run our constants file. So when I do run the simulation, I'll also run the constants file first, like so. So when I just wrote the constants in here, it didn't actually put them into the MATLAB workspace over on the right here. So MATLAB didn't know what those values were. We also need to make b in the first place. We didn't do that. So we'll call that the damping constant. And that will be b. And let's just make it 10 as well for now. So the units of b have to give us acceleration units when it's multiplied by velocity units. So if we do the dimensional analysis on that, let's go back to this screen for a minute. I know that negative, actually I just care about the value, b over m times x dot has to end up equaling units of acceleration. So if I write out the various dimensions for that, the units of b I'll leave as unknown. The units of m I know are kilograms because it's the basic SI units. little brackets there, so I'm looking at the dimensions. And velocity is, of course, in meters per second. So this has to equal units of acceleration, which are meters per second squared. So if I rearrange this, I can figure out what the units of B are. It's kilograms times meter per second squared times seconds over meter. Another way you could write that is as kilograms, or sorry, newtons, because a kilogram meter per second is a newton, meter per second squared, over meters per second. So just like the spring constant tells me the force per unit displacement, the damping constant tells me the force per unit velocity. All right, back on Simulink, I can add those units here. Might seem pedantic to do that for just these 3 units, but if we have hundreds of units that are all changing sometimes, we'll want to keep track of what's what. All right, so back here, now I have the constants file run, and I have the mass spring model run. Let's hit that. All right. Fail to resolve unspecified signal dimensions. That means I probably didn't set something right. Let's go back and see what's wrong. Undefined function or variable k. That's because when I added my constants here, I only added b and m. Let's add k as well. You'll notice that Simulink is pretty good down here at telling you what the problem is. It actually tells you exactly what line in what block something went wrong, which is pretty similar to how a lot of other IDEs will tell you what specific line of code something went wrong in. So we'll have k right here. And just like with the other variables, I'll go to the function bar, edit data, and I can just make this a parameter as well. All right. We'll go back home and save that. Again, it takes much quicker to save now. And let's head back over to here. Let's see if I resolved all the issues. So we can see it's still running because it says stop right there. Open it, finished. So I can see my outputs here are, in the workspace, all those variables I defined to make the simulation. And then answer right here is a 1-by-1 simulation output. So the simulation output is basically a class. And in that class, it has member variables for a lot of the important information coming out of the simulation. If I open this particular simulation output, I can see it has 3 fields. Tout, which is the time, simulation metadata, which we'll ignore, and error message, which is empty because no error occurred. So that's not very useful because I didn't actually get out what my position was from that. So to get out what my position is, I'll go back over to Simulink. And if I refresh this by hitting Control S, let me just click around, yeah. It still says it can't see these, but it's lying. Probably if I close and reopen the model, it'll turn them from red again. Yep, there we go. They're happy now. So the last thing I have to do is I have to make sure the variables I care about are actually sent out of the simulation. I want to send them back to the workspace. So I can do this by logging my signals. So I can right-click and type log selected signal. And when I do that, I'll click that little piece here. I get a little dialog in the property inspector where I can set the signal's name, and I can set how often I log that signal. So I'm going to make this signal name DDX, because that's my acceleration. You can also make test points on these signals, which can be useful for debugging. I'll log this signal as well. Again, we'll click it. Oops. I don't really want to do that. Why is it mad at me? There it is. Oh, I have to open Property Inspector, not Data Inspector. That's the problem. Properties. Okay, there we go. And we can see the various parameters of that right here. The problem with these signal loggers is that they're really hard to see which signals are being logged. And what it's trying to do is it's trying to put the data into this like built-in simulation data inspector tool, which is not super useful in my opinion. So that works. You can log signals that way. There's also a little bit more overhead than the other method we'll use. The better method is to just use to workspace blocks, which look like this. So what I can do is I can just use this like a normal Simulink block, and I can route my data to that. And then I can change the name of the Simulink block to whatever my variable is. This does the same thing as logging, but with less of the overhead. So I'm actually going to remove these log points because I don't really encourage you to use them. I just wanted to show you that that exists. Because one benefit of the log points, it makes your model look cleaner because you don't have all these various signals floating around. Let's see if I can remove this log point. You're going to be mad at me. Mad because I'm clicking too close to that. Come on. Let me get rid of the log point. Properties. Probably should have figured out how to get rid of the log point first. All right, we'll leave the log point alone. It's not hurting anyone. I'll figure out how to get rid of that later. It's kind of funny. It goes to show that I don't use log points very often. Let's add the to workspace blocks for the other two variables. We'll add one for dx. I really just care about my position and my velocity. So those are the only two I'm going to get. All right. So back over to my main page, I have to save this too. Back over to my main page here. I'm going to give myself some different initial conditions. If I give myself a higher initial condition, what I'll expect is the block will oscillate back and forth. So I can run that. And it ran the simulation, but it's still not very helpful to access my results. So what I need to do is I need to put these results into a variable. So I'll say results equals this. And now all my results will get plopped right in here. Another trick I can do, I'm not very happy with all these error messages right here. Those were error messages from older runs, but they're still clogging up the terminal because the terminal isn't being cleared every time I run my code. To fix that, I can just add a couple lines. I'm going to add CLC. That clears the command window. I'm going to add clear all, which clears all my variables. And I'm going to type close all, which will close any open figures. Currently, it's a little bit upset at this one because it's technically not the best performance to redefine all these variables every time. But if you're running a lot of different scripts, some of which have just scratch paper basically in them, it can really clutter the workspace. So I like to use clear all. So if I run this again, we'll get a couple things. First of all, we'll clear our command window nicely. Second of all, if I type results here in my command window, I can see that results now has dx in it and x in it. It also has these logs out fields, which are from the data logging signals that I can't remove for some reason. But we're going to ignore those for now. It won't hurt anything. So dx and x are what I'm after. The way we access things inside a structure like this in MATLAB is by doing dot notation. So if I want the variable dx in results, I do results.dx. And it tells me that dx is actually a time series with the name dx, and it has one variable for time and one variable for data. So that's great. I would like to plot this all without worrying about it. So I'm going to define a function to plot all these results. Let's call it plot results, and it just should input the variable results. All right. So there's a trick we can do with these various time series where I can check if a certain field in them exists. So I can use the isField command, and I can ask for results.dx. Oh. Let me double check the correct way to use this function. This is why it helps to be organized. I remember exactly where I used this function before. And so I can go navigate right to that document and find it. Let's see. Plot outputs. So I have to type the name of the variable, and I use isMember, not isField. So if I try that again with my variable dx, I can say isMember dx in result.who. And that gives me 1, which means dx is inside it. So the other thing I can do is I can say isMember, let's say v. I didn't name the variable v, so this will output 0 because that's not a variable that exists. All right, so back over here, let's go back to my right folder. If you try to run the script, it'll actually prompt you to change back to your current folder, so you don't really have to spend a whole bunch of time navigating the file system. And if I do that, see I just changed folder right here. So it doesn't plot results because I haven't defined the function plot results. So to do that, I need to make another script. I'm going to name this script plot results. And inside this, I'm going to define the function plot results. The way we do that is by typing function plot results. And then we specify any inputs that go out of it. And to end the function, we type end. So the only thing I want going into my results function is the results object. The first thing I need to do is I need to run that check to see what fields are inside results. So I'll type fields equal results.who. Who checks all the different fields that are inside results. The last thing I can do is I can just say if the variable I care about, x, is member of fields, then what I'll do is I'll create the plot. And I'll fill in that code in a minute. And then I also want to see if dx is a member of fields. And then I'll create the plot there too. So the obvious question is, why do I need to do this? Why can't I just use the fields that I know are inside this results object? And the reason is, if I had a much bigger simulation, I might have a whole bunch of workspace blocks that are spitting a whole bunch of variables to the workspace. And I don't necessarily have all of them turned on at once. So there are a lot of cases when I can run my simulation and a certain field won't actually exist here. If I called plot results and it didn't check if the thing was in a field, it would just throw an error and waste my time. So by defining it like this, I can make sure it just tries to plot the members that actually exist in the results field. So I can make that plot by doing plot. The first thing I want to do is I want to extract the data. So to get the x data, I need to get results dot x, there it is, dot data. And I want to squeeze this. What squeeze does is it just eliminates any extra fields that might have been added there by Simulink. It doesn't always happen, it's good practice. And then I want to make sure x is a column vector, because I like always working with column vectors. And the way I do that is like so. So now I know this vector is n rows and 1 column, where n is the number of time steps we got. I can do the same thing for t. I can get results.x.time, and I'll also make time a column vector if it's not already. Last thing I need to do is I need to plot it, so I'll plot t and x, and I'll create an x label, and I'll create a y label. All right. One more helpful thing to do, I'll add the word figure right here. This keyword just tells MATLAB to open this in a new figure right here. And I have one too many. Oh, this needs to go inside. If is member x fields. There we go. I need to fix that down here too. All right, now MATLAB is happy with me. All the errors went away. I'll do that same thing here, except instead of x, I'm going to use dx. And I can actually just copy paste all this code. I want to make sure instead of using x, I'm looking at dx. So I need to replace all the x's with dx. And I can actually do that quickly by hitting Shift-Enter. But if I do that, it's going to replace all the ones above it. So instead, I'll just hit Shift-Alt-Enter, and that will only change the ones that occur below it in the text. Pretty helpful. All right, now this is not a position plot, so I'll call it velocity instead. All right, let's hop back over to init now, and I'll run this. So this time I get some figures. So I can see my velocity and my position. So I can see my position looks a lot like what I expect from a mass spring damper. We get these spring oscillations, but they steadily decay towards 0 because of that damping. What I can also do is I can go to my constant and I can set the damping to 0 and run that. And if there's no damping, we see the oscillations never die down at all. They just keep repeating. Looking at that plot, I realized I forgot titles. And because I have my code nice and organized, I can just click back to the function that has all the plots in it, and I can just add my two titles. Velocity versus time. Titles changed by units. And over here, position versus time. Okay, so that's great. I have a system that is apparently behaving like a real mass spring damper, and I'm able to get the results from the simulation, and I'm also able to plot them. The next thing I want to do is I want to control this simulation. But before I do that, I want to address the problem in my file system. Currently, I've just been dumping every file into the workspace for my project. And the issue with that is it's going to fill up very fast if I have a very big model that could have dozens or hundreds of scripts and files in it. So I'm going to organize. I'm going to create a new folder in here called source src. And then I'm going to take constants, init, my mass spring model, and plot results. I'm going to drop them all inside there. That little dialog that popped up was just the project making sure my moving files didn't break anything, which is a helpful feature to have. You notice I didn't move this mass spring model.slxc. That's just the cache file for the Simulink model. It basically saves a bunch of data about your model. So when MATLAB runs it a second time, it doesn't have to reload all the information that it already calculated that didn't change between runs. So you can just leave this file alone. It's typically added to your git commit, so you don't actually save that file day to day. And if you delete that file, nothing bad happens. It just gets regenerated the next time Simulink runs. All right, let's hop over to SRC and do a bit more organization. I want a good place to put all my useful functions that I'm just going to access whenever I need them, but I don't need to edit them day to day. I'm going to call that utils. And I'm going to move plot results into utils. I also want to keep my models separate. So I'm going to say models and drag my model in there. This is a bit silly for this project, so I only have one model. But if I had a project with many models, this would be very useful. And the final project I need, or the folder I need, is experiments. Experiments gets constants and init in it. All right. So the reason I call this experiments is because a constant file and an init file define the full set of unique parameters for the simulation. Everything else doesn't change in a different simulation test case. It's all just math or utilities. So what I can do is I can create lots of different constants and init files with lots of different sets of initial conditions. So I can test a whole bunch of different simulation test cases without manually editing the same init every time. All right. Now, if I go back out all the way to this project folder right here, it looks a little bit cleaner. Now, there's going to be an issue if I go ahead and run this. we'll see it can't find the model. The reason it is because init lives inside the experiments folder, and models lives a level up, then a level sideways in the models folder. Now I said the project would handle this all for us, but I have to tell the project which files I actually care about, so it doesn't track a lot of extra garbage. I'll go back to my main root folder for my project, and I'll right-click on the src file. I'll scroll down and I'll hit Add to Path, and then I will hit Selected Folders and Subfolders. Additionally, down here, I can, in the project browser, I can click on this folder and I can add that whole folder to the project. This does two things. First of all, it makes it so when I run this, it doesn't break. There we go. And then the second thing it does is makes it so when I use source control at GitHub, it'll automatically keep track of all these files. Let's see. So yeah, this is just a little bit mad because I moved the files around after it already loaded them in memory. The simplest fix to this is just probably close and open MATLAB. I can probably also clear all, close all, and CLC. That might fix it. Other thing I could do if I want to make it kind of boot itself is I can go ahead and close my project and then just open the project again. All right. Oh, look, and it actually gives me a option to fix these shadows models right here. It's just in save or discard changes and close all shadowed models. I believe it just wants, oh, it actually just wants me to close this. So I'll close that. And I bet it's happy now if I run this simulation. Yep, there we go. So the issue it was mad about was I had the model open and then I moved it. So that confused MATLAB. But if I open my model now, it won't give me any issues. All right. That is the plant model done. Let's go ahead and add the controller. I'll start by uncommenting this out. And I'll go ahead and fill in the inputs and outputs like I did before. Referring to my block diagram in my notes, I know this needs my desired position, x asterisk or x star. I just copy and paste it there to make another block quickly. It needs x, the position, and it needs dx, the velocity. And the only output here is whatever my force should be. All right. So what I would like to do is I would like to set it up so that my position goes through a PID controller to try to control the position towards 0. So I'll go ahead and delete this trace here, and I'll double click, and I'll add a PID block. So there we have it. Inside this PID, I would like to pass in the state error, which means the difference between my desired state and my current state. So to do that, I will go ahead and create a subtraction right here. And I will subtract x from x star from x, I mean. So now the thing that comes out of here is my state error, my position error. Let's call that x sub e. I also would like to drive my velocity towards 0. But we'll see in trying to control the position, we actually will drive the velocity to 0 anyway. So I can actually ignore this for now. If I want to do a different kind of control that incorporates this velocity, I could do that too. So I'm going to go and delete this for now because I don't need it. And I'll just use this position PID. All right, I need to pass out my force F as the output of the PID. So what I want to do is tune the constants in this PID, the P, I, and D, until it gives me a system response that I'm happy with. Currently, I'm going to leave them at the default values. P is 1, I is 1, D is 0. And I'm going to try to make it so I can use the auto-tuning of MATLAB to figure out the best way to tune this automatically. All right, Let's go ahead and close that out and head back out here. I can now replace my constant 0 with the force coming out right here. And I can bring my x and my dx, or sorry, my x star as well. For x star, I'll just define this as a constant, but I want to define this constant as a variable I can define in the workspace, like so. All right, clean that wiring up a little bit. So this I'm pretty happy with. Let's see what it does. X star does not exist. So X star sounds like a initial condition or simulation parameter that changes simulation to simulation. So I can just add it as an argument in my init file. And let's say I'm trying to drive the pendulum towards a position of 0. Now the pendulum, or the mass spring. The mass spring already wants to go to 0, so that won't really do much on its own. It should just drive it to 0 slightly faster, depending on the values of p, I, and d we pick, of course. All right, so at first glance, it doesn't appear to have made much of a difference. So let's see what happens if I want to drive it to a different position, like 1. All right, so I can see the value it's approaching here in my position plot. If I click on that, it's now going a little bit towards 1, although it's not super convincing there. I should probably graph like a horizontal line at 1 so you can see that. Let's try to set it somewhere more aggressive. 5. All right, so we can see, check this out. It's getting towards 5, but it's doing a pretty bad job getting there. It's at 2, it's slowly climbing. If I ran this for a long time, it would probably get there. But that's not really what I want. I want a more aggressive approach. The reason it's going so slowly is because I chose just the default values for my proportional coefficient and my derivative coefficient. If I head back to the Simulink, I can do a couple things. I can change those manually, or I can attempt to auto-tune those. Not every model can be auto-tuned. There's some setup that's required to do that. Let's see if mine happens to be auto-tunable by default. It's loading, I believe. All right, so the PID tuner is kind of glitched. It created the window, but it didn't actually open it on my screen. We'll just have to navigate to it. All right, so check this out. It's actually going ahead, and every time I drag these sliders around, it's trying to simulate the step response of my system to see what happens. And you can see for some combinations, my system becomes unstable. So I think I don't really care about a super fast response time. I would just like it to take maybe 2 or 3 seconds to respond. So this looks about right. And then let's say I want it to be very aggressive. So I want it to jump as quickly as it can and be okay to oscillate back and forth. If I want this to be more calm, I could turn it to more robust, and then I'll get a much nicer, well-behaved approach. Let's make it real aggressive though. I'll hit update block. So check this out. It automatically picked the P, I, D, and filter coefficient it thinks will give me this performance that I desire. Oftentimes these values will just be your starting point, and then you can tune those more, but this should be good enough for now. I'll go back out here, head back over here, and run my init. All right, so in the figure, I can see we are much more rapidly approaching 5. I'd like it to be even a little bit faster. So let's go back to my auto tuner and make it happen. Here we go. I want it to be as fast as I can without it actually diverging. Just like that. Now, the obvious problem with this is that it's going to output a really large force right here, which my real system might not be able to handle, but it's okay for our toy model. The way you fix this would be to add a upper and lower bound to the PID, which you can do over here in saturation. All right, so back over here, let's run this. And there we go, much better. We start at our position of 10 and jump almost immediately to 5. If our system is more realistic, let's say we have an actual limit to how much force we can apply, we can do that by hitting Limit Output in the Saturation tab, and let's say my force is actually limited from -5 to 5 newtons. Or actually, that backward, the upper limit goes on top, like so. I could also define those as variables in my init script or constants in my constant script. Run it again. And there we have it. It looks a little bit more reasonable. It takes about 10 seconds. You can see the effect is pretty dramatic when I limit the force the PID is allowed to output. It calms down a lot. Let's up my time span just to make this a little bit more interesting. All right, so now I can see a little bit more about what the graph does. It oscillates a little bit, then quickly stabilizes to this position here. 0.5. Did I say 0.5 is my x star? Why is it going to 0.5? Let's see what's going on here. If I remove my saturation, is it still happy with us? Yeah, okay. So I'm guessing what happened is when I added the saturation, I also needed to retune the controller because it's now trying to output a bunch of forces that it actually can't do. Let's see if that's the case. I have to apply my changes first. I'm gonna do that. All right, so jumping over here, we can see it actually just changed those values on me. So the reason it did that is because it now sees a different plant model than the values it originally picked. So to tune to these various parameters, it needs different values. If I update the block here, we see they jump around some more. Let's see if that does a better job. It's still trying to go to 0. Did I do something silly in here? Or in here? All right, we'll deal with that in a minute. The important takeaway there is that the real system with saturation limits is going to behave very differently than the other system dynamics. So that's why these PID values that we start with are just starting guesses, and we'll probably have to adjust those a lot to make them work with saturation. So that's why it's so important to build a realistic model so we can capture these effects in simulation before we get to hardware. All right, for the sake of time, let's not worry about that for now. And go back to this response we're happy with. All right, there we go. We get towards 5. So making this controller work is great. However, there's still 2 more organization things I want to do. First things first, inside this model right here, I have code inside this dynamics block that's just like manually typed in here. And the problem with that is if I want to edit the code in this block, it won't get updated in lots of other places. So what I'm going to do instead, I'm going to define a function ddx I'm going to call it mass spring dynamics. And it's just going to intake all the same variables that my function block intakes. And I'm going to go ahead and copy this line of code to my clipboard. So now what I'm going to do is I'm going to right-click on this function and hit open. And that'll create a new function. And I'll just type in function edx equals mass spring dynamics of all the variables I had right here. I'll just copy this name. Oops. All right. And now in here, I just need to write in the dynamics equation I found earlier. I just erased it from my clipboard, so I'll just type it in real quick again. There we go. All right. So the benefit of this is this mass spring damper function can now be placed in my utils folder and reused across many different models. I'll just add it in there. And I can see it now is going to be, if I had multiple models that called this dynamics, they could all use it without any issues. The other thing I'll do is, let's say I want to reuse a whole subsystem. Maybe I'm trying to control a lot of different mass spring dampers with a lot of different controllers, and all I'm really interested in doing here is reusing the same plant every time. So I can do that by right-clicking on the plant and going to Subsystem and Model References. And I'm going to create a referenced subsystem from this block. I'll do that, and I'll just name that plant. So you can see right here, our plant gets these two little lines here and here. That means it's a reference subsystem that can be shared across multiple models. And if I head back over here, I see it showed up right here. If I open this new model, all it has is the reference subsystem that I care about. So what I'll do now is I'll go back to my SRC folder, and I'll make a new folder called Reference Subsystems. Reference Subsystems. Enter. And I can go ahead and move my new subsystem reference over there. All right. The last thing I need to do is I need to go ahead and make sure all of these things are added to my project's search path. So I'm going to right-click on the SRC folder, and I'm going to say Add to Project Folder, including contents. And it'll ask if I want to add all these things, and I'll hit Yes. Notice I do that in the Project menu, not in the File menu here. In the File menu, I can add stuff to the path manually, but it will only be added to the path every time if I add it in the project here. So if I go back to my project object right here, I can go to the project tab, hit settings. I can see right here that I've added to the path SRC referenced subsystems. And what I would like to do is add everything in SRC. So I'll just click that. So I can see now it adds SRC, SRC experiments, SRC models, and SRC utils as well. Hit apply there. And now if I close out and open up MATLAB, it'll still remember all those preferences. All right. I would love to goof around with this for another hour and figure out what the glitch is with not glitch necessarily, the mistake is with the PID tuning. But we'll just leave it as the kind of unrealistic controller here that can output a huge amount of force to cause it to converge really rapidly. That's not too rapid, actually, about 4 seconds. And then we will leave it at that. So in summary, we have our initialization file that sets up all the conditions for this specific simulation instance. Initial conditions, desired states, simulation parameters, and then it finally runs the simulation, and it saves the results to an object called results. Then plot results goes in, and it plots all the variables in that result structure that we care about. The other file we have is constants. That defines all the various constants of our simulation. Now over here in this folder structure, We have our source folder, which has our experiments. We have our models folder that has our mass spring damper model. We have our reference subsystem that has the plant model. Now I can reuse this plant model in any other model I might want to make. And if I update the plant in any of my simulations, it updates in every simulation. So if I want to make a little change, I don't have to do that in every simulation manually. Finally, I have my utils folder that I'll put all my helpful scripts in. The last thing I'll show here is what this looks like in our Simulink plant. So here is the project structure for the Simulink plant. You see it's got the SRC folder. It's got a couple other things going on here. But inside the SRC folder, you see all the usual suspects. There's my utils folder with a lot of functions. There is my test folder that will have tests in it, nothing yet. There's a startup folder that runs some calculations. There's a reference subsystem folder with a few subsystems in it. And there are a couple models here. So over the course of the year, we're going to fill out all these folders with a lot of different information. So the contents of this will grow and grow, which makes the organization so important. You can also have the project automatically become a Git repository, but I don't want to do that right now. But that's kind of nice because you can automatically track and save all the folders in your files. All right, so that's it for the demo. I will post this video as an unlisted video to YouTube and link it in the controls channel. And then I will also, once I make it a little bit prettier, I'll add the Simulink demo to a GitHub repository for reference. All right, bye.